Transformations, things that turn that pre-image into the image. What are the different things you do? Casey? So reflections are one. Okay, dilations are one. Translations are one. Contractions. Rotation. Stretches. Okay, and compressions. So some of those are the same thing in our course. So we don't do rotations because by stretching, compressing, reflecting, we can basically do what we need to do with a function. And there's no place in a function that actually rotates it a different direction. You actually have to switch x and y for that to happen. You can't just do something to the existing x and y. So when we talk about reflections in or transformations in our course, we're not going to do rotations because on an xy plane to rotate something, you have to actually switch x and y coordinate type of things. That's not going to happen for us here. Okay, but the rest of the things you guys said are going to happen. So we have these different categories, okay? So one category or one type of transformation, like you guys said, is translation. So just on the back of this purple paper so that it's with the information, we're going to talk about translations. So what does a translation do to the graph? Good. You can move that pre-image to be the image in any direction, but like sliding across the graph, right? So you can go left, right, up, down, but the points all stay the same distances apart. They keep their shape and all of that kind of stuff, okay? So translations are basically going to be shifting our graph, okay? So if you like to think of it that way, now, when you guys wrote the formulas for this in geometry, you had two separate coordinates that you dealt with, the x and the y. We deal with that here, but we are now looking at a function, and we're supposed to be able to tell, based on how the function is written, if there is a translation, and if it is along the x-axis, left and right, or if it's along the y-axis, up and down. Okay, so the way that we're going to see our transformations, we're going to write it with some notation, and then we're also going to give you an example of an equation, okay? So, for example, ours are going to fall into two categories. We're going to have our horizontal translations. So if we're moving horizontally across the graph, which coordinate is affected for each point? The x coordinate, okay? With our functions, absolute value, greatest integer, these other functions that you saw, the x is inside of the function, right? It's inside the absolute value bars, or it's inside the greatest integer function brackets. So if there is a translation that affects x, you're going to see it inside of your function. So this is like the function notation for it. Whatever your function is, squaring, radicals, absolute value bars, there's going to be some number in there subtracted from x. And this subtraction is going to be part of our formula, okay? So examples of this, if we have a parent that's like y equals the absolute value of x, and we wanted to shift it or translate it right 3 spaces, what do you think this new equation would look like? So you start with this. What do we have to write into that equation now to show that it's translating right 3? Good. And we saw this when we did our investigation, right? It said x minus 3 in there, but it actually moved the graph to the right 3. So we established, okay, mathematicians aren't totally crazy. They put the minus in the formula because then we can see what the h is, and knowing what the h is tells us what to do. This is an h of positive 3, and that moves our graph to the right 3. Okay? So vertical translations mean you do the absolute value or the greatest integer or whatever it is like you normally do, and after you've calculated that part of it, then you add something to it. So we saw this in our investigation with absolute value as well. So if our parent function is still y equals the absolute value of x, but now we want to translate, sorry, I didn't spell it right, up 3, what would our new function look like? So starting with this same parent function, but now we want to translate it up 3. Marcus? Yeah, so we have that part there, but what is it going to look like specifically if we're using the absolute value function as our parent function? Good. So is everybody good with translations? This is basically how they work. Okay? So then we can shift things up, down, left, right. All right, the second transformation we're going to talk about are reflections. Okay, so you guys mentioned reflections. We're going to look specifically at negatives affecting the x or affecting the y. So we're not going to reflect over different lines. We're only going to reflect over our axes because we're only going to be adjusting specifically the x's changing sign or the y's changing sign. Okay, kind of like you saw with our step function and with our absolute value function as well. Okay, can I change? Any objections to me taking this off? Okay. I have to use this. Sorry. I did not let my little move. Okay, so the second transformation that we're going to look at are our reflections. They're in no particular order of importance, just kind of breaking them up into category. So reflections, you can kind of think of as like flipping over something. And again, in our specific purposes, we're going to see things flip over the x-axis or over the y-axis because we're just changing x or y coordinates specifically. So again, they break up into these two categories. There's the horizontal thing that can happen, or there's a vertical thing that can happen. Now, when I use the word horizontal and I'm talking about a reflection, that means it's changing from left to right or right to left. So which axis would you be flipping over? The y-axis. Good. So if it's referred to as horizontal, that's the same as saying over the y-axis, which is a more common way to state it. But horizontal stuff affects what coordinate? The x-coordinate or the y-coordinate if you're reflecting horizontally? It affects the x-coordinate even though you're flipping over the y-axis. So in your function or in our function notation, we would say we're changing the sign of the x-coordinate. So you would see it written inside of here saying that those are changing. Okay? And so an example of that, if we had a parent function that was y equals the square root of x, and we wanted to have this reflection over the y-axis, any idea what we would rewrite our function as? So if this is our parent function, how could I adjust the function to show in its equation a reflection over the y-axis? Oh. So I have to be careful though where I put the negative. Do I want it before the function is done or after, depending on this? So if I say that this is flipping over the y-axis is just changing the sign of the x, I want to change the sign of the x before I apply the function. So I'll have my square root, I'll have x. Will the negative go in front of the square root or just in front of the x? In front of the x, okay? Because you're changing the x-coordinate and making it have the y-coordinate that used to be with the other. If you put it out here, you're finishing the calculation of square root first, and you're changing it after you've already completed the function, after an input would have already been changed to an output in the parent function. Okay? So what you guys were saying before, if we're going to put the of the radical like this, that's doing this, applying a negative once the function has been completed. Once you've already done the square rooting or the absolute valuing or anything like that, that is a vertical reflection, which is really a flip over which axis? The x-axis, because you're going from up to down or from down to up, which is flipping over the x-axis. Is this all right for reflections? Anybody opposed to me changing the screen? So then you guys said words like dilations and stuff like this. So basically we kind of group all of those into one category. And we just call them, they're either stretching or compressing. So if they're getting bigger or further away from the vertex in that one direction, they're being stretched. If they're getting closer to the vertex in that one direction, then they're being compressed. Okay, so our third category, or the third piece of language that we're going to use, is going to be this category of stretches and compressions. So again, there's a way that these show up horizontally, and there's a way that they show up vertically. And again, the horizontal changes tend to happen to x before we've applied the function. So it's something that's in there with x before we're doing the absolute value, or before we're doing the square rooting, or squaring, or greatest integer. Okay? So with horizontal cases, this number is inside the function multiplying x. Okay? When it's changing vertically, your greatest integer function is a really good example of this. When it's changing vertically, okay, think about what kind of action moved the steps vertically farther apart. There was a number outside the brackets, right? And that number multiplying the brackets moved them further apart, meaning for the vertical stuff, you had your greatest integer function, and there was a number in front of them that was causing that change, that changed the vertical distance. This number inside the brackets with x changed the horizontal length of the step. Okay? Now, these split into two categories. Okay? The number that's multiplying x, first of all, if it's 1, it doesn't matter, because that's not really a new number multiplying x. That is what is in our parent function, right? Just 1x. The number could be smaller than 1. Sorry, that should say 1. I said 1, but I wrote 0. So the number could be smaller than 1, or the number could be bigger than 1. And I guess I'm talking basically about the absolute value, because if b is negative, we're going to treat that like two different transformations. The negative part is going to be a reflection thing I'm going to do. The number part is going to tell me what to do here. Okay? So when I say the absolute value of b is less than 1, so think about our example would be something like this. What happened to the horizontal length of the greatest integer function when 1/2 was in here multiplying x? Yeah, the horizontal length actually got bigger. So if you think about the endpoint of the step being 0, 0, and you think horizontal direction, because we're talking about something horizontal right now, if this was your original step length, by putting the number 1/2 in there, did my step get stretched or did it get compressed? It got stretched. So the horizontal stuff is a little crazy, right? It's h, but it's like minus h. This one says 1/2, so your brain really wants to do something with 1/2, but really what's happening to the step length is it's getting stretched out longer. It's getting multiplied by 2 instead of 1/2. Okay? So this is a horizontal stretch, specifically by a factor of 2 if you want to include that to help you remember that you're using the reciprocal. So basically this number right here is not the b value, it's the reciprocal of the b value. It's like using 1 over b. Instead of 1/2, use 1 over 1/2, or 2 over 1. Jonathan? And 0, yeah. Like the absolute value. It can be negative. It would, but it wouldn't. You got to remember there could be other things in there, so you can't just take the negative off, because what if something's being added later or something like that, okay? So when you look at your b value, it could be negative, and the number. But the negative is going to go back to being a reflection. So if there's a negative there, you're going to treat that like a reflection. So in absolute value, that one doesn't matter, because when you reflect horizontally, this goes over to here and this goes over to here, and you see no change. But in other functions, it will matter. Okay, so it depends on the function type. So this is just talking about the number. That's why I put the absolute value bars around. Okay? All right, so an example of b being greater than 1 would be like when we had a 2 there. Okay? And when we had a 2 there in our greatest integer function, what happened to the horizontal length of our step? It actually got shorter, right? So if we think about this being the original picture on our graph, what happened is it got pushed back towards the vertex point, or compressed horizontally, right? So this actually caused a horizontal compression. Things were getting multiplied by 1/2, not by 2. Our step used to be 1, now it's only 1/2. Okay? And again, that's because here we're using 1 over b. So the way I remember this when I'm trying to like memorize how all these things work, honestly, all the horizontal stuff is like a little bit crazy, right? It's x minus h instead of x plus h. So when it says x minus 3, I'm actually going to the right 3. It says times by 1/2. What's actually happening on the picture of the graph? Things are getting double the length that they used to be. The vertical stuff is much more straightforward, right? Like we saw with our greatest integer function. With vertical stuff, again, we can have the same thing. And again, I'm going to talk about absolute value. If this is negative, go back to reflections and do the negative as a reflection, and then use the number part here. A can be smaller than 1, or A can be larger than 1. But again, remember, A is outside of the function. So the example here would be a 2 outside of the greatest integer function. So what happened vertically to our graph of our steps when all of a sudden a 2 showed up outside of here? Chris? Good. The distance between the steps got larger. So think about vertically. Did your graph get stretched, or did it get compressed? Stretched if the distance between them increased. So since we know this is adjusting our graph vertically, and we know when we're multiplying by something it's a stretch or compression, here we know that this is going to be a stretch. And basically, the normal distance between the steps was supposed to be 1, but it got changed to 2. We basically times to that stuff by 2. Okay. Jonathan? Yes, I'm saying the absolute value because I'm telling you if it's negative, go back and do the reflection. So if you have like negative 2 as the A value, you have 2 transformations there. You have a reflection, and you have the 2 that's going to cause this part here. Okay? All right, so the other option is if that is like a 1/2. So when we put a 1/2 there, it took our normal parent function and did what to it? Compressed it vertically, right? The vertical distance between the steps became only 1/2 instead of 1. It did nothing to it horizontally if that was the only thing. It just compressed it in the vertical direction. So this is a vertical compression. And physically, just so we know what to do when we're graphing, that means our distances that used to be a certain amount apart are getting kind of cut in half, or times by half the distance they used to be. Okay? So is this okay for the idea of what's happening there? All right, so turn over and look at number 1 on your paper, and then I'll tell you what you guys are going to do here. And you guys will have the remainder of the time to do this. And then your homework tonight will revolve around this idea. So at the top of your page, it gives you this idea. So if something had everything going on, it would have numbers in all those A, B, H, K spots, right? And there'd be a lot for us to do to get it graphed. Then the directions say, given that f of x equals the absolute value of x. So for the problems below, you're going to use this idea. Write each function below and then list the transformations from the parent function and graph the function. So your first problem says this. So I'm trying to get you guys used to 2 things at the same time. Not just how to do a transformation, not just what happens when I plug numbers in here. Hopefully we're getting better at that. But also how to understand function notation and write it correctly. So the first problem says g of x, the function you're going to graph, g of x, is equal to, and they say f of x minus 5. This is function notation. You don't know what to graph yet, right? Unless you know what f is. But you do know what f is, right? It told you right here, f of x is this guy. So if they tell you that they want you to be working with f of x minus 5, how does this get rewritten? The name of it is f of x minus 5. What's it going to look like as a function? Brandon? But you can't keep the f there anymore. Remember, this is the name of something. So this is saying go use your f function, but rewrite it with this transformation in it, x minus 5. Marcus? Not the absolute value of x plus 5.
Would it just be inside brackets x minus 5?
Good. Look back at the notes that we just said, right, about transformations. Writing inside of here x minus 5 just really means they want your h value to be 5, right? They want the number being subtracted from x to be 5. So if this one is my f function, I am still doing greatest integer, but instead of just having x inside of it, I should have inside of it x minus 5. Then you guys are going to graph it, and you're going to say what transformation took place. Does anybody know, just by the fact that this is the new equation and that was the parent function, what transformation is taking place right here? Jonathan? What type of transformation? Translation, okay. And exactly how many units, which direction? Chris? Not up 5. Sarah? 5 to the right. Good. So your transformation here is that this is a translation 5 units right. How do I know that it was to the right or to the left and not up or down?
Because 5 is your h.
Good. 5 is your h. It's inside the function affecting the x. The stuff that affects the y, the stuff that goes up and down and is vertical stuff, will be outside of your function. It will not be inside of whatever function you're trying to work with. Anything in here is a horizontal type of change. Anything out here is a vertical type of change. Does that make sense to everybody? Yeah, Natalie. Yeah. So remember, this is just the name of something. This is saying go to the f function, so go to this guy, and rewrite it instead of using x, subtract 5 from the x. So if the f function was named in the directions to be the greatest integer function, then this is going to be the greatest integer function, but with 5 subtracted from x inside of it. So all of your equations for this entire page, they use the same function from the directions, f, which is a greatest integer function, which means all of your graphs on this paper should be what kind of function? Greatest integer function. Okay? They should all be greatest integer function. All right? Okay, so start that, and then if you guys want, I'm going to have kind of a little cheat sheet, not a cheat sheet, a site you can go to on Desmos to quickly see the greatest integer graph if you guys want to see that, okay, without having to graph it all by hand.